All right, these are the work and power slides. All right, so before we get to work and power, we just need to review energy. So energy is the capacity to do work. So we know that all forms of energy are scalar, which means only magnitude, no direction. And the unit for all forms of energy is the joule. So we looked at the law of conservation of energy, and it states that energy cannot be created or destroyed, only changed or transformed from one object to another. Uh, and it can be transferred. So, but it can also change or transform into other forms of energy. Now, mechanical energy these are special kinds of energy. It's the energy due to the position of something or the movement of something. And the three forms of mechanical energy are kinetic energy, potential energy, and there are two forms of potential energy. So, gravitational potential energy and elastic potential energy. So if you add all these up, you'll get the total mechanical energy of an object. Now, this comes into play a little bit later. So roller coasters are an excellent example of going from potential to kinetic, kinetic to potential. So let's answer this question, though. Why won't a ball bounce to that original starting height? So to do this, we did the destroyed energy lab. And if there's a question mark, spoiler, energy does not get destroyed in this lab. So if we drop each of the objects from a height of 100 centimeters and measure the height of the object, the bounce to, we use the equation to calculate the percent of that energy that was transformed back into gravitational potential energy. So we dropped each of them from 100 centimeters and we measured the height that they bounced to. And you notice that the percent transformed, well, is that final height, right? It's like the percentage of the final height that it bounced back to. And we'll figure out why that later. So let's just talk about the types of energy that this ball has. So the instant it lets go, it only has gravitational potential energy. Now, as it's in free fall, it has kinetic and gravitational potential energy. That gravitational potential energy is being transformed into kinetic energy. Now, the instant like it's touching the ground, just before it starts to compress, it's all kinetic energy, right? It doesn't have a height, but it's moving. That's the fastest point that that ball is traveling. Now, once it's at rest on the table and it's being compressed, all of that mechanical energy is elastic potential energy. Now, as it's bouncing back up and moving back up, well, it's going to have kinetic and gravitational potential energy. It's at a height and it's moving. And once it reaches the maximum bounce height, it's going to be all gravitational potential energy. Now, let's take a look at these again. Why didn't the mass of the object need to be known in order to calculate the percentage of the original gravitational potential energy that was transformed back into gravitational potential energy? So let's take a look at that. We know that once you start it, you only have gravitational potential energy. Once it bounces back up, it only has gravitational potential energy. So if we're taking the final mechanical energy, that bounce height, divided by the initial, well, at both of those points, the elastic potential energy and kinetic energy are going to be zero. All I have are the mechanical energy. Now, once it bounces, it comes back up, the masses are going to remain the same. Gravity is going to be the same. The only thing that's changing is the height. So if you take that final height divided by that initial height, that'll get you the percent of that original mechanical energy that was transformed back into mechanical energy. And we know that that bouncy ball was able to convert most of that energy, or a lot of that, yeah, most of that energy back into mechanical energy. But let's look at this final question. Energy cannot be created or destroyed. This would mean that a ball that bounces should return to the original height it was dropped. Explain why none of the original objects bounce back to their original height. Well, yeah, as it's going down, gravity is transforming that gravitational potential energy into kinetic. As it's moving back up, gravity is transforming that kinetic energy back into gravitational potential energy. The bottom is elastic potential energy. But if you drop a ball, you'll be able to hear it, right? So some of that mechanical energy is changing into sound. Some of it's changing into internal energy, right? And that energy doesn't go back into that ball as mechanical energy to get it back to that original height. So we're losing some of that energy to the outside world. So we looked at the law of energy or conservation of energy, and we said changed or transformed. Well, those in the real world, those could be synonyms of each other, but when we're talking about energy, those are two different things. So when energy changes, the total mechanical energy will increase or decrease, right? That number will change. That's how I remember it. So that can happen for one of two reasons. Well, an external force increases the total mechanical energy, and energy loss due to an external force, like friction, decreases the total mechanical energy. Now, when energy transforms, It transforms from kinetic to potential or potential to kinetic, but the total mechanical energy does not increase or decrease. So let's answer this question though. Why doesn't the Newton's cradle go forever? So this is the Newton's cradle. So an example of energy being transferred from one object to another, right? Remember, energy like momentum can transfer is, well, you can see that that energy is being transferred back and forth to each of those ball bearings. Now, an example of energy being transformed. So that means going from kinetic to potential or potential to kinetic. Well, as it's falling down, that gravitational potential energy is being transformed into kinetic energy. As that ball bearing's moving up, well, the kinetic energy is being transformed into gravitational potential energy. But gravity is not causing the mechanical energy to increase or decrease. It's just transforming that energy. Now, energy being changed. Well, it initially starts at rest. Whoever lifts that up, well, that's an external force that's increasing that mechanical energy. Now, every time those ball bearings hit, you can hear it. And so some of that energy changes into sound. Every time it hits, that frictional force will turn it into sound. And that doesn't come back to getting that ball bearing back up to the original height. Some of it's lost to heat. There's like tension in the rope. There's like internal friction that energy is being lost to the outside world. Now, you could eliminate sound, right? You could put this in a vacuum, but eventually it will still come to rest because that energy is still being like every time those ball bearings hit, it's turning into heat, right? So that energy is changing into heat. So now let's go over what causes energy to change versus transform. Well, conservative forces transform energy, right? So energy is stored somewhere in like a field. So there's going to be some like potential energy associated with this. So the big one that we use is gravity. Now it's path independent. Now what that means is that if you're standing at a height or something's on a table, that has a gravitational potential energy. It doesn't matter if somebody lifted it straight up or went up the stairs or went up a ramp. At the end of the day, that's how much gravitational potential energy there is on that object has. Now, examples of conservative forces are gravity and the spring force. So, or yeah, so elastic force or something. But we just mostly focus on gravity. That's the big one. That causes energy to transform. Kinetic, potential, potential to kinetic. Now, non-conservative forces, they change energy. So unless it's like an external force, like an applied force, giving that object some mechanical energy, energy is going to be dissipated as heat, sound, internal energy, etc. So it's path dependent. What that means is that if you slide an object on the table, well, if you slide it back and forth more and more times, you're going to generate more heat. More of that energy is going one way. It's being dissipated out. Now, friction is the big one, right? Most all other forces, though, uh, are non-conservative forces other than like gravity or like a tension, or not a tension, so elastic force. All right, so if we look at this, right, let's look at a skier going down a ski. So at the downhill part, right, you'll notice that if we wait for this graphic to start over where they're at the top, if you'll notice as that skier is going down the hill, right, that green bar, that total mechanical energy remains the same. So the energy is going to be transforming, right, because we're going from gravitational potential energy to kinetic energy. Now, this question is what force is pulling the slider down the slope? It's going to be gravity. Gravity is what's causing it to transform, and gravity is going to be a conservative force because it's path independent, and it's storing that energy, and that energy is being released as that skier is going down the slope. Now, as the skier hits this unpacked section of snow, notice what happens to the total mechanical energy. Well, the total mechanical energy is going down. So the energy is going to be changing, right? And the friction is what's causing that energy to change. And friction is a non-conservative force. That energy is being dissipated out into the world, right? And that's not coming back as mechanical energy. So back to the original question, right? So we did this one, right? Who can do the most work by running up the stairs as fast as they can? So we did the stair challenge lab. So if we look at this, the challenge of the lab is to pick the person in the group who can do the most work by running up the stairs as fast as they can. So I run this and I carry Bob. I carry a big anvil, right? So one person in the group will be running the stairs. Now, these are the rules. You cannot have a running start. You must start from a complete stop. Cannot skip more than one step at a time. Cannot touch the handrail, so you can't pull yourself up. But you can touch your handrail to guide yourself or stable yourself. Time starts with the person whose timing says go, and time stops when both feet touch the top of the landing. So You decide to yourself who's going to be competing in the stair challenge, which group member will be timing the stair challenge, and then once we do that, time how fast the person ran up in the stairwell. So let's take a look at what this means by doing the most work by running up the stairs. So if you apply a net force to an object, that object will change its motion. It will accelerate. If an impulse is applied, then that momentum will change. Now, if work is done on an object, then the energy of that object will change or transform. Now, work is a scalar quantity, and this is the equation for it. You take the absolute value of the force. So it's the scalar product of force times displacement. Now, force and displacement are vector quantities. Now, multiplying vectors gets a little bit tricky. There's different ways to do it, but this is the way that you do the scalar product. You take the absolute value of the force multiplied by the absolute value of the displacement multiplied by the cosine of the angle in between those two. Now, this looks very complicated, but it actually gets very simple. Now, to do work, three conditions must be met. Number one, a force must be applied. Number two, that object moves in some displacement, and some component of that force is in line with the displacement. So it causes some of that displacement, that energy change. So let's take a look at when no force is done. Well, obviously, if there's not a force applied, there's no work done, right? If it doesn't move, if there's no displacement, no work done. But let's look at when the cosine of the angle is 0. So perpendicular components, 180 degrees, right? Or sorry, 90 degrees, my fault. 90 degrees, perpendicular components applied to forces displacement do no work. So work can also be positive or negative, right? So you probably think, well, how can this be possible if if work is a scalar quantity? Well, look at the cosine graph, right? So cosine of the angle is going to be -1 if it's 180 degrees. So this is just a simpler way to think about it, right? Positive work is done if the force is applied in the direction of motion, the same direction of motion. Now, negative work is done if the force is applied in the opposite direction of motion, and no work is done if the force is applied perpendicular to motion. So the example is like tossing a ball, right? So if you're tossing a ball, you are applying a force in the same direction of motion. You're doing positive work. Now, the other example I use, like just think about it this way. You're giving that object energy. You're doing positive work on that ball. Now, somebody catching that ball, well, they're applying a force in the opposite direction of motion. They're doing negative work. Think about it this way. They're trying to take that energy away from that ball. So in general, like this is just sort of a general rule. Just think about it. If work is done on a body, if work done on a body is positive, then that force is trying to speed that object up, right? If work is done on that body is negative, that force is trying to slow that object down. So let's get back to who won that stair challenge. So I said, well, calculate the amount of work done to the person in your group by climbing the stairs to a height of 3.5 meters. Well, if we look at that, right, well, just think about it this way, right? So let's look at stairs. As a person is walking up the stairs, the mechanical energy will increase, right? You're increasing the gravitational potential energy. Energy is changing. You're changing that chemical potential energy stored in your body into gravitational potential energy. At the very top of the stairs, that person has gravitational potential energy. Now, gravity is a conservative force. So it doesn't matter that that person went straight or walked up the stairs or would climb up a ladder. At the end of the day, if they're at that height, they have mass, gravity's pulling on them, they have gravitational potential energy. It's path independent. So it doesn't matter what path you take. At that height, they're going to have that. So we can calculate that. That actually makes the math easier. So how could the person at the top of the stairs release that stored gravitational potential energy as kinetic energy? Well, they could fall down, right? If they fall down the stairs, that's going to release that gravitational potential energy. So let's take a look at the scoreboard. Now notice, like my score, I was carrying Bob, that big anvil. And notice, well, my work is large. Now, here's what you need to understand is that time plays no factor into how much work it does, right? So everyone, like, students like run up as fast as they can. That does nothing. That does nothing to increase the amount of work that you do. So it's just the force applied multiplied by the displacement multiplied the cosine of the angle. So the force applied, the force that you have to apply to go up the stairs is your weight. Every time you have to lift your weight up, the displacement of the stairs. So to get your weight, what you do is you just take your weight in pounds, multiply it by 4.45 to get your weight in newtons. That's the force. The displacement is 3.5 meters straight up. And you don't have to worry about the cosine of the angle because it's straight up, right? The force is in the same direction as the displacement, right? So you can see all the other ones, and this one, well, I won, right? So I won in this one as well, right? So this one, somebody else won. Now, if we look at this one, as the person is climbing the stairs, that we know the mechanical energy is changing, it's increasing, right? Now, was the force fighting against? It's going to be gravity. Gravity is a conservative force, and that means, well, it's path independent, right? So now this is the key to the whole thing. Which person who competed had the most amount of work done to them climbing the stairs to a height of 3.5 meters? How much work was done to them? Explain how this person won the challenge. Well, in most of the classes, I won, and that was because I was carrying Bob, right? So that I was carrying that big anvil. I was carrying more weight. I was applying a larger force up the same displacement of those stairs. We all went to the same height, but I gave myself an advantage. Even though I acted like I didn't want to do it, I gave myself an advantage by carrying Bob. Now, let's take a look at power, right? So power is the measure, like let's look at time, right? So power measures how fast work is being done. If something has a lot of power, it means it does a lot of work in a small amount of time. Power is the ratio of work done to the time taken, and that is the equation right there. Power equals the work done divided by that time interval. So power is defined to be how fast work is done and is measured in the unit watts. So if you apply a force of 1 Newton over 1 meter for 1 second, you have delivered 1 watt of power. So you've probably seen the watt on a light bulb, right? So think about it this way, right? If you have a 60-watt light bulb, that means that every second that light bulb is like changing 60 joules of energy into another form, or electric energy into another forms of energy, like heat and light. Now, 25 watts, well, that's going to be a lower rate, right? So I like to think of it as you can think of how fast it's changing and transforming that energy. So like sort of like a speed limit, right? So or a speed, right? You're going 60 miles per hour, was 60 watts. That's like 60 joules per second. Same thing with like 25 watts or 25 miles per hour. It's like a speed. How fast is that energy changing or transforming? So if I ask this question, who can deliver the most power by running up the stairs as fast as they can? Well, if we look at those scoreboards again, and I just highlight that, we'll notice the fastest person, yeah, they did deliver the most amount of power. But the person that did the most, but that doesn't mean they did the most work, right? If we look at this period that did this, we'll notice the fastest person didn't deliver the most power, right? Or do the most work. I did the most work, and I also delivered the most power. Now, this period is interesting because this can happen. Well, notice the fastest person didn't deliver the most power. Notice that the person that did the most work also didn't deliver the most power, right? So depending on how this challenge is phrased, you can have 3 different winners, right? If it's for time, work, or power. Now, this one, you can have a winner that sweeps it all. The fastest person did the most work, which means they delivered the most power. So let's answer this question though. Why can't you jump to the top of Mount Everest? Now, this might seem like a silly question, but everybody eats enough food. Everybody eats food, right? So the unit that food is measured in is the calorie. Now, 1 calorie of food is 4,184 joules. Now, if you took 2,000 calories, the amount of food that one person eats in a day, well, if you were able to change all that energy into gravitational potential energy, that would put that person at about 8.4 miles. Now, Mount Everest is 5.5 miles above the sea level. So you should be able to jump from sea level to the top of Mount Everest. You have enough energy stored as chemical potential energy in your body. But the thing is, you're limited by biology. Your muscles cannot deliver enough power. They cannot change and transform that energy fast enough. If they could do that in the time that it took you to like squat down and jump up, if they could transform and change all of that energy into gravitational potential energy or kinetic energy, right? So you'd have to launch up to the top. Well, you could do that, but your muscles aren't powerful enough. They cannot transform and change that energy fast enough to jump that high. That's why there's a limit to how like high a person can jump. So we did the Big Mac challenge to start measuring power. So the challenge of this lab is to burn off a Big Mac as fast as you can by lifting it to your mouth. You will do this by computing the power you deliver. The average Big Mac has a mass of 0.25 kilograms or a weight of 2.5 newtons. You will simulate this with the mass that is given to you. Follow the directions below to calculate how long it would take you to burn off a Big Mac by lifting it to your mouth. So the idea is that every time you're lifting something, well, you are delivering power, right? So you're delivering power to your muscles. You're transforming. You're changing that energy from chemical potential into like kinetic and gravitational potential energy. Well, energy in a Big Mac is stored. How long would you have to lift a Big Mac up to your mouth in order to burn that off? So the first thing that you do is you find out who's competing in your group, who in your group will be counting. So somebody is going to have to count the number of reps they do in 100 seconds. So then what you need to do is you measure the displacement. So we need to find the work. If we're going to compute the power, how fast that person is converting energy, what you need to do is you need to measure the displacement. We know the force is 2.5 newtons. That's that next question. Well, now the displacement is from their arm when they're holding that mass that'll simulate it, all the way extended, all the way contracted. That's going to be different for everybody though, and it comes out to around like 0.6 to 0.7 meters. That's a good range. Some people have like 0.75 meters. All right, so let's answer these questions. All right, so after we did that, what we did was great. We calculated how much work they did in one rep. So every rep they're doing that. If it was 2 joules, they're changing 2 joules of energy every single rep. Now, we did this for 100 seconds. So then once we know the total amount of work that that person did, we just divide it by 100 to get how fast they're transforming that energy. So the faster they go, the more power that they're going to deliver. So this is how this is how you calculate the amount of power, how fast they can change that energy. So this was the key to it. According to the McDonald's nutrition information, a Big Mac contains 560 calories. A calorie is another unit for energy. 1 calorie equals 4,184 joules. So there was a Google Sheets where you just enter the amount of reps, the amount of work done, and it will automatically calculate how long. So it comes out to like 1 to 2 weeks, right? Depending on how fast that person is lifting that object up to their mouth, right? So the question is, what force is pulling the mass down? Is this force conservative force? So it's going to be gravity. Gravity is pulling it down. Now the force is going to be path independent. So that brings us to this next question. Well, the mass will not be traveling in a straight line from fully extended to fully contracted. It will travel in a curved motion. Will this have any effect on the gravitational potential energy the mass has by the person's mouth? The answer is no, because gravity is going to be a conservative force. It's path independent. So it doesn't matter that that person's curling it. At the end of the day, well, that Big Mac has gravitational potential. It doesn't matter that it takes a curved path or straight up. And if your group were to redo the Big Mac challenge, how could you improve the time? This actually was supposed to be, how could you improve the score? How could you improve the power, right? If you could pick another person to compete, who would you want to pick and why? So if we look at the equation for work, the force is set. That's going to be the weight of the Big Mac. That's 2.5 newtons either way, right? But the displacement was what we measured, right? So every single time somebody does a rep, well, it's going to be dependent on the displacement. So if you pick a taller person, the one with the largest like arm span, every time they do rep, they're going to be doing more work. So they can, if they do the same amount of reps as somebody else, well, they're going to be more powerful because they're transforming more energy or changing more energy every rep that they do. So just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.